Hey guys, I'm Arturo, and today I'm going to talk to you about the singular value decomposition, or the SVD. And my mentor was Justin. So I'm going to introduce the singular value decomposition and show you guys how to calculate it. Then we're going to talk about something called the truncated SVD and how it's used for approximations. And then I'm going to talk about two of the applications it has, which are image compression and um, analyzing voting tendencies. So the SVD is a generalization of the eigenvalue decomposition. So it's a generalization of it because the eigenvalue decomposition can only be performed on square matrices with full rank, but the SVD can be performed on any matrix. We're interested in the SVD because it can obtain a low rank approximation of any matrix. And because of this, it has many applications that I already mentioned, image compression and identifying people with similar voting tendencies. So formally, the SVD of a matrix A is U times sigma times V transpose, where U and V are orthonormal and sigma is a square diagonal matrix. So the columns of U are called the left singular vectors and the columns of V are called the right singular vectors. And the diagonal entries of sigma are called the singular vectors, and they are ordered decreasingly. So the top left entry of sigma is going to be the largest entry of sigma. And now how to calculate the SVD of a given matrix. So first we have to remember that the eigenvalue decomposition of a square matrix is what you see. And we're going to try to do something similar for non-square matrices. So first, we can find the eigenvectors of A and A transpose and A transpose A, and these are square matrices. So we can do this by doing the eigenvalue decomposition. And then if we assume that the SVD exists, which it can be proven that it does, we can substitute it in for A. And then since V and U are orthonormal, V times its transpose is going to equal I, so it cancels out. And then we have U times sigma transpose, which is a square matrix times U transpose, and that will give us the eigenvalue decomposition of a non-square matrix, or a generalization of it. So U is the eigenvector matrix for A transpose and V the one for A transpose A. Then we can normalize all these vectors and write out the following sum, where all the sigmas are square roots of the eigenvalues of A transpose and A transpose A, and these eigenvalues are actually equal for any matrix. So finally, we can get A equals U sigma V transpose. So now I'm going to talk about a different way to write the SVD called the truncated SVD. So the truncated SVD is the same thing as the sum you guys saw earlier, except that it's only the first K parts of the sum. It's not all of them. And this is useful because if any sigma is small enough, we can discard the term and the value of AK will be affected negligibly. So it's a good approximation of A, and it uses less data because we removed a whole part of the sum. And actually, it's a really good approximation. In fact, Eckert and Young proved that it is the best approximation of a rank K. And so what's a rank K approximation? It means if you take the norm of A minus B, where B is a rank K matrix, the time where that's the smallest is when B equals AK. And now I'm going to go into some applications that we covered on our project. And a really good and intuitive application that will show how powerful the SVD is image compression. So first, you have to know that computers store matrices, images as matrices, where each pixel's color is represented by a number. So here we can see like black is 0, white is 255, and as you increase the number, the lighter the shade is. And for colored images, it's the same, but with red, blue, and green, and there's 3 matrices, and you just do it once for each of those matrices. And the truncated SVD can be used to approximate the matrix that generates the image. And this will save memory while affecting the quality negligibly because it is a really good approximation. And so here we can see how good of an approximation it is. So on the y-axis, we have the error of A minus AK. And on the x-axis, we have the rank of AK. And we can see that, you know, like at 400 here, the difference is like, I can't see like a real difference between 400 and 800. And even like at 100, there's a really little error. And here it is visualized. We ran a MATLAB code where we compressed images, and here we can see where AK is rank 10 and the original image is rank around 1,000. And even at rank 10, like if you know what SpongeBob is, like you will know what the image is. And at rank 25, the quality increases pretty noticeably. And then at 100, it's really good quality. And at rank 250, the quality is basically the same. Like it's the same image in my eyes. So that shows the power of the SVD. Like you store basically the same image with 1/4 of the data. And now we're going into what was my favorite part about the project, voting tendencies. I really like this application because it's like a non-science application, which is really interesting because most applications that we hear of are science-based. So we can use the SVD to compare members' voting tendencies. So by this I mean like members of Congress or the Senate. And we can do this by turning voting data into a matrix. So I did this analysis on the Puerto Rican Senate, and some background on the Senate is that there are 30 senators and there are 4 parties represented in the Senate. There are, I believe, 21 senators in one party, which is called the PNP party. There are 7 senators in the PPD party, 1 senator in the PIP party, and 1 independent senator. And this is what the voting data we used looked like. So here we can see the name of the senator, and at the right 2 columns we have bill numbers and how that senator voted on that bill. So a favor means yes, and contra means no. And we turn this into a matrix by using a Python code, and this is what the matrix looked like. Each senator has their own row, and each column corresponds to a bill number. and the entries are 1 if the senator voted yes on that bill number, -1 if they voted no, and 0 if they abstained or were absent. So now we have our matrix and we can use the SVD. So we perform the SVD on the matrix, and then we can take the first two singular vectors and plot them. We take the first two singular vectors because they're the most important ones, since the singular values in sigma are ordered from greatest to least. And this is what the plot looks like. So on the left, we ran this on the matrix of all the bills for the term, and we can see that there's two clusters, and on the bottom you can see all of the blue dots that represent all of the senators from the PNP party, and on the top left we can see another cluster where all the other senators are. And you know, this makes our results promising because it makes sense that all of the senators from one party voted one way while all the other senators voted differently. And the plot on the right are bills in which most of the we took a subset of all the bills in which most of the senators voted the same way. So here we can see there's only one cluster, and this makes sense because if all the senators voted similarly, then the data should show one cluster because the senators voted similarly. And the last thing I wanted to talk about was, before that, so this is a graph of the singular values of the voting data. And here we can see that the first two singular values are much greater than the rest of the singular values. And this is why graphing the first two singular vectors can be very useful. And lastly, I wanted to talk about the error plots for each of the applications. So on the left, we have the error plot for the image compression, and on the right, we have the error plot for the senator's data. And we can see that the image compression one goes down really quickly and levels off, while the senator's one is linear. And this is because in the matrix for an image, so if you take any pixel, then the surrounding pixels are nearly identical in its value because the color of an image pixel is going to be basically the same as the one next to it, while in our senator's matrix, any entry in that matrix is surrounding matrices which correspond to different bill numbers or different senators vote on the same bill. They have nothing to do with each other, and we can't predict or correlate anything with the bill with the entries next to it, which means that if we remove an entire rank of that matrix, we are losing information that we can't really predict or approximate, and that's why the error is linear and the error on the image goes down really quickly. But if we had a random image where each pixel was just random, then we would see the error of that image be linear. And that's it. Thank you.